Welcome to problem solving session for Introduction to Group Theory. Today we will discuss problems related to syllabus from week 5, that is problems related to internal direct product, normal subgroups and normalizer of a subgroup. And I'm Siddhi Balu Ambore from IIT Gandhinagar. So let us start with our first question. Question 1. I hope I'm audible and visible. If you have any doubt or if there is any problem, please let me know. Okay. So first question, let G be an abelian group and K belongs to Z. Then the map A from A going to A power K, that is, this is group operation applied K times on A, is an isomorphism if K is A minus 1, B 0, C 2, and D 3. So this is, and here they have said it's isomorphism. So I hope what isomorphism means. I mean, you know what isomorphism is. If not, so let me quickly give you the definition of isomorphism. So let G comma dot and H comma star be groups. Then F from G to H star is called group homomorphism if for all A comma B in G, F of AB is F of A star F of B. This is definition of group homomorphism. And if F is both injective and surjective group homomorphism, then F is called isomorphism or group isomorphism. Okay, so for this elements here, the only information given to us here is G is an abelian group. That's it. And we need to find, and this K is some integer, and this map is like A going to A power K. So it's like A is going to, if my G is with respect to multiplication, then it is A multiplied K times. Or if it is with respect to addition, then A is going to A added K times. Okay, so this is what is given to us. So, what is your guess for this? That for what K? So options given are A minus 1, 0, 2, 3. So note that A 0 first of all. A going to A 0. So by convention, A going to A 0. A 0 is considered as identity element. So if the moment I have my group as non-identity group or non-trivial group, this will not be an isomorphism. Okay, so note that A power 0 is E, where E is an identity of group. Then A going to A power 0 means A going to E for all A in G. So therefore this therefore A, let me call this. Therefore A going to A power 0 is not an isomorphism if G is not equal to E. In this case, when we are writing this map, this is map from G to G again. Okay, so this is map, let us call me this map as phi from G to G, okay? And says that A is going to A power K. That's it, A power K, or yeah. So this is what we are doing. So first, this one is not correct, that A going to A0 will not be an isomorphism whenever my group is non-trivial group. Of course, when my G is a trivial group, that is a group containing only identity element, in that case, this will form an isomorphism. But here, the statement is very general. They are saying that G is only an abelian group. It could be of any cardinality, anything. We just have to find whether when this A going to A power K is isomorphism, for which K this is isomorphism. So first, so we know that this is gone. I mean, A going to A power 0 is not helping. So what about this first option, A? Let me just write this. A is my A going to A power minus 1, first option. So this actually gives us an isomorphism. A going to A inverse will give me an isomorphism since G is an abelian group. Okay, so I just need to check whether, first of all, let us check whether this is isomorphism, this is group homomorphism or not. So what is phi? Let us give, let us define this, that it is from G to G such that A going to A inverse. Okay, and so check first whether this is, to check phi is group homomorphism or just homomorphism. So whenever I say homomorphism, it is group homomorphism. So phi of, let A comma B in G, then phi of AB is AB whole inverse, which is B inverse A inverse. But since given that G is an abelian group, we can shuffle them and we get that phi of, or we can just write this here, and phi of A is equal to phi of B, sorry, into phi of B. So therefore, phi is definitely a group homomorphism. Now we have to check whether it is injective and surjective. So injective, I hope for a group homomorphism is injective if and only if the kernel of this group homomorphism is a trivial subgroup, that is only identity element. So it is like, so if F is injective, group homomorphism F is, or phi, let me write, P is injective group homomorphism if and only if kernel of P, that is all those X in G such that P of X is identity, is my trivial subgroup. Okay, this is the condition for injectivity. So here what my phi is, my kernel phi is, for in given case, let me write this is in bracket, kernel phi here is X in G such that P of X is E, that is all those X in G such that X inverse is identity. But X inverse is identity when? When does that happen? It happens only when X is identity itself. Because then what? X inverse is identity. Then if I take again inverse on both sides, it will be X is equal to E inverse. That is just E. So this becomes trivial subgroup. Okay, so therefore P is injective. Now we just need to check whether phi is surjective or not. Okay, so now to check phi is surjective. So in order to check surjective, we have to choose one element from the codomain and we have to find an element in my domain such that its inverse is that original element which we chose. So let y belongs to G. Then since y is in G, y inverse also belongs to G, right? Then y inverse belongs to G, right? Since G is a group. Then P of y inverse will be what? Y inverse, but that is just y. So therefore, for y in G, we have y inverse belongs to G such that phi of y inverse is y. Therefore, phi is surjective as well. So therefore, from since it is homomorphism, we checked it is injective and surjective. Therefore, P that is G to G such that A going to A inverse is always group is always isomorphism when G is abelian group. Okay. Any doubts here for this statement? So this one is true. A going to A inverse. Can this be true? If A going to A square, can that give me group isomorphism? So homomorphism and everything is fine in this case because G is abelian and everything works. But I mean, in for P of AB, so if my phi is from A going to A power k, then P of AB will be AB power k. Then since we are in abelian case, I get this B power k. This is phi of A into phi of B. That's not a problem. So homomorphism is not a problem. We have to only check. This is true for any k, for any k in Z. Or this is not correct way to write. Let k in Z plus or Z. And phi is from G to G such that A going to A power k. Then this is always a group homomorphism. That's not a problem. So, but is this A going to A square? Is this isomorphism? Can you give me any counterexample, or is this always true? Anyone has any idea like how, or any counterexample which you want to suggest or give? So we can take simply this, right? G is equal to K4. Uh, I hope you know this group E, A, B, C such that A square, B square, C square is E, and AB is C. Okay, then in that case, if I take phi from G to G such that A going to, or let me take G going to G square in this case, then phi of A is A square, which is E, phi of B is B square is E, phi of C is C square, that is E, and again phi of E will be E anyway because we are dealing with an isomorphism. So this is definitely not a isomorphism. Okay, so, and this is abelian group. Okay, this is abelian group. We are in abelian group. So therefore, phi from G to G such that A going to A square need not be an isomorphism. It could be in some cases, but in this case, it is not an isomorphism. Is this okay? We were asked this question in general sense where G is any abelian group. Okay, so this definitely gives us that it is not an isomorphism. Okay, so this one is not true. Now the third one, again, can you give any group of such that A going to A cube? And we have to check whether this is isomorphism or not. Any counterexample? This is also is not true because what main thing here is that once I have an element in the group of order k, that element when I raise it to power k will go to identity, and the moment that happens I lose the injectivity of my group homomorphism, and in that case it is no more an isomorphism. So you just have to came up with the or choose a group which has elements of order 3. So the moment I have that, that element, when I raise it to power 3 or when I like multiply it 3 times or add 3 times, it will give me an identity element and it will no longer be an surjective map. Sorry, injective map. And that will give me that it's not a group homomorphism. Okay, so any group which you know which has elements of order 3. I mean, Z3 to Z3 will be very trivial, but apart from that, you can take S3, right? Or this for now, you can, for now, let us take Z, G is equal to Z3, and then phi of which is 1 bar, 0 bar, 0 bar, 1 bar, 2 bar, and phi of 0 bar is anyway 0 bar. Phi of 1 bar is again 3 bar, which is 0 bar, and phi of 2 bar is 6 bar, which is 0 bar in Z3. Okay, so therefore P is not isomorphism for this G. Okay, and in general, you can take G is equal to S3, and then we have three elements of, I mean, we have 3 cycle, and in that case, those 3 cycles will go to identity element, and then again, it will not be isomorphism. So that's it. So you can choose any group of your choice, and in general, any for any k, keep this in mind, for any k, a power k, when I take, The moment I have elements of order k in that group, it will go to identity, and that will just make this map no more not isomorphism. Okay, so that's it. Any doubts here? Any doubts? So this again, a power 2 and a power 3 is not will not give us isomorphism. If you have any doubt, please ask. Otherwise, we will move to next question. So consider H is 3 power A, 6 power B, 12 power C such that A, B, C in Z, which is a group under multiplication. Okay, this is group under multiplication in Q. We can, or in Z itself, doesn't matter. Okay, and no, if they are considering it a group in, no, we are considering it as a group in Q. Multiplication in Q. And Q star, in fact. And let this 3, 6, and 12 be, I mean, these are the groups generated by 3, 6, and 12 be the subgroup of Q star. Q star is Q minus 0. I hope you all know. Again, Q star is under multiplication. And generated by, as I said, they are generated by 3, 6, and 12 respectively. Okay, and we now define a map. Now consider the map Phi from 3 cross 6 cross 12. So this is direct product. Let us call this G, or this to H. So this is my group in, this is my subgroup in Q star cross Q star cross Q star, or Q cross the multiplicative subgroup of Q, and so on. Okay, so this is, this is not star, this is cross. And this and it is defined as phi of, this is 3 power A, 6 power B, 12 power C going to, or is equal to 3 power A, 6 power B, 12 power C. So this is different. This is a tuple in this group, subgroup of this Q star cube. I can write this as Q star cube. Doesn't matter much. Okay, and no, let me write. Let's keep it as it is. So then, which of the following statement is true? We have to check. Then A, phi is injective. B, phi is not surjective. And C, phi is homomorphism. And D, none of the above. So this is the question asked. Group under multiplication. So I hope you all know what this means. This is just 3 power A such that A belongs to Z, and this is variable subgroup of Q star. So because 3 power A into 3 power B is 3 power A plus B, and 3 power minus A is inverse of p power a. Okay, or let me write this 3 power a inverse is 3 power minus a. The powers are in Z. Similarly for 6 and 12. Okay, so these are subgroup of this Q star under multiplication. Any doubts here? The way it is defined, and my phi is from this, and phi of any element is of this form here. 6 power b, 12 power c. I mean, this is tuple, and it is 3 power a, 6 power b, 12 power c, and now this is in Q star. This is some number. This is some rational number. Okay, so what we have to check whether phi is injective. So can phi be injective? Is phi injective? Please feel free to ask doubts if you have any. Yeah. So we are asked whether phi is injective or not. So is it injective? To check whether phi is injective. So we have 3, 6, and 12, and here it is just a number. So just take basic numbers which you want. So for example, see phi of 3 power 1, comma 6 power 0, 12 power 1 is what? 12 is 36, and this 3 power 0, 6 power 2, 12 power 0 is again 36. So definitely this cannot be an injective map because these 3 power 1, 6 power 0, 12 power 1 is not equal to 3 power 0, 6 square, 12 0, but we have p of, let me just, but we have these two as equal. Okay. And if you want to see it as some element belongs to kernel or not, in that case, you can write this, that this element. So we want, so these two are equal. So we want to kind of want to choose inverse of one of them. So we can have this 3 power 1, 6 power minus 2, 12 power 1 is what? 3 power 1, 6 power minus 2, 12 power 1, and which is 3 into 12 by 6 square, and this is 1, which is my identity in Q star. Okay, so therefore kernel of P is not just identity as this element 3 power 1, 6 minus 2, 12, 1 belongs in this group, in the kernel of this map P. So therefore phi is not injective. Therefore phi is not injective. Any doubts here? You can also find all the rest expression of this kernel. Okay, it will, there are many ways to write those, and well, so it's definitely not injective map. Is it? Now they are asking whether phi is surjective or not. Okay, so they want to us to check whether, to check that phi is not surjective. So is phi not surjective? Is there any element which does not have pre-image? So H has this kind of element. H is my this 6 power, sorry, 3 power A, 6 power B, 12 power C, such that ABC in Z. Okay, so is there any element in this H? And my phi is from, let me call this as G. So let us denote G is equal to this. Phi is from this G to H. So is there any element in H which does not have pre-image? In G? Note that any element here is 3 power A, 6 power B. Let for any, it's trivial. 3 power A, 6 power B, 12 power C in H. We have this 3 power A, 6 power B, 12 power C in this in G such that, let me write alpha or G such that P of G is 3 power A, 6 power B and 12 power C. So it is surjective. So this one, that P is not injective, is again a false statement. Okay. And now the third part, whether phi is an homomorphism. Yes, it will be homomorphism because phi, what two elements of this group G look like? It is some 3 power A1, 6 power B1, 12 power C1, and 6 power A2, sorry, 3 power A2, 6 power B2, and 12 power C2. This belongs to G. And phi of, let me call them G1 and this one as G2. This G1 and this is G2. Then phi of G1 into G2 is 3 power A1, 6B1, 12C1 into 3 power A2, 6B2, 12C2. And since we are in Q star, which is abelian, we can just shuffle and we get this phi of G1, G2 is 3 of A1 plus A2, 6 of B1 plus B2, and 12 C1 plus C2. And this, when we split, we get a, no, this is not correct way. Phi of G1, G2, first of all, what is G1, G2? G1, G2 is A1 plus A2, 6 B1 plus B2, and 12 C1 plus C2. And now we will separate them. Okay, and it will be 6 B1, 12 C1, and A2, 6 B2, 12 C2. And now this is phi of G1 and this is phi of G2. Okay, and we got that phi is in homomorphism, is group homomorphism. So any doubts here? So this third statement is true and we got what we needed. Any doubts here? That how phi is a group homomorphism? Okay. Okay. If there is any doubt, please let me know. Otherwise, we will move to therefore phi is homomorphism. I hope this one is also clear. How the multiplication in that group G is working. Okay, it is just component-wise multiplication. And now question 3. Let G be a group. So G is any group. And let H be a subgroup of G generated by the set S is equal to X inverse Y inverse XY such that X comma Y in G. Then which of the following is correct? We have to check this. And the options are that H is not a normal subgroup of G. B, that G by H is not abelian. C, if G quotient N is abelian, then H is not a subgroup of N. And I will also explain what these statements mean. If K is a subgroup of G and H is some H is subgroup of K, then K is normal in G. So this is the question. So first they are asking, so what is that H is actually generated by this elements of this form, X inverse Y inverse XY for XY in G. Okay, and what they are asking is that whether H is a normal subgroup or not. And then next they are asking is that whether G quotient H is abelian or not. And then they are saying that if G quotient N is abelian for some subgroup N of G, then that H is, then they are asking whether this H is contained in N or not. Because that, what does this mean? H is not a subgroup of N. So they want to know whether this H will always be contained in any such group, any such subgroup N of G or not. And last statement is that if K is a subgroup of G and it is given that H is contained in K. So note that my K is here, H is here, and G is here. This is just a subgroup of G. And what they have given is that H is just contained in my G. And we know that we have some information about H and G, and they are asking whether if H contains K, then this K becomes normal subgroup of G or not. That's the fourth option is asking us. So let us start with the first question. So let me just move this here a bit. Here. Okay, and question. So A option, we have to check whether H is a normal subgroup or not. Okay, so how to proceed? We are given this information. What are the definitions or what are the ways to show if something is normal or not? So the simple is like if G is in G and H is in H, then we have to check whether G inverse belongs to H or not. Right? This is what we do in order to check whether given group is a normal subgroup of G or not. Okay. So clearly this G inverse belongs to G, right? Because G is in G and H is in H, which is anyway subgroup of G. So this is here. And H is here. So H inverse also belongs to since and H inverse belongs to it. So, mm, so we have this H inverse, G inverse. This belongs to G, but from the definition, so what my H is, let me write here again explicitly. H is generated by X inverse Y inverse XY such that XY in G. Okay, this is what we know here. But the moment I have element of this from where G, H are everything in my group G, this implies this H inverse. Let me write this properly. H inverse G, H, G inverse, this belongs to H, right? Because this H inverse, this G here is what? G inverse inverse. This element is in H, so this implies by quotient or just the property of subgroup, we have this G, H, G inverse belongs to H, H, right? And the moment I have this is anyway my H. So this G, H, G inverse, this is anyway subset of H. So this belongs to H. So I started with any G in G and H in H, and I obtained that this G, H, G inverse belongs to my H. So any doubt here? How this is happening? Or if you do not want to like do anything here of this sort, you can also from here just do this. We know that this H inverse G, H, G inverse belongs to H. This much is clear. Now what we can do is just pre-multiply by H there. H is anyway in H. So H, so this whole thing, since H is a subgroup, this whole thing will still be inside H. So since H in H, this H, H inverse G, H, G inverse, this will belongs to H, right? And this will give me that G, H, G inverse belongs to H because this becomes identity and I get this. Any doubts here now? But by definition of H, this H inverse GH. Any doubts here? This is, if clear, please let me know. I assume that it's okay. If not, please ask. We just use the fact that the expressions of this form are in H. That's it. And we started with GH G inverse in G. So we anyway GH G inverse belongs to G, but we now finally obtain that GH G inverse is in H. Okay, so I hope this was clear. If not, please ask. Otherwise, I will move to second option. So second option is that whether G is G quotiented by H. So therefore, G is what we got here is therefore H is my normal subgroup in fact. Therefore, this first option is false. H is a normal subgroup. H is normal subgroup. So now this G quotient H makes sense. Okay, and now they are asking whether this G quotient H is abelian or not. To check whether this key G quotient H is abelian or not. Is not abelian, I think they are asking, but that's okay. How to proceed with this? So we have to check whether this is abelian. So elements are here are of this formula. That X H Y H belongs to G quotient H. And to show X Y H is equal to Y H Y X H or not, right? This is how multiplication works. What we need to show is wait, let me write it explicitly. X H Y H is equal to Y H X H or not. But by multiplication in the quotient, we have this. Okay, But note that if we have this, then this will give me that yx inverse xy is equal to h, right? And this is what x inverse y inverse xyh is h. And this is true because anyway, element of this form belongs to h. So this has to be equal to h. So if we backtrace it like this anyway happens. So this is true. So my G quotient H is anyway a normal subgroup there. Any doubts here? Because this is true, right? So this has to be true here. All these statements are equivalent. Any doubts here, please let me know. This here, this element here, this belongs to H. Now the next is that we have to check that the, the third statement is that if this one is not true, I mean G quotient H is actually abelian. We just saw that, and they are saying that if G quotient N is abelian, then H is not a subgroup of N. So given that the third statement contains two parts, if G quotient N, given that G quotient N is abelian, to check or to show that H is a subgroup of N or not. Okay, so G quotient N is abelian, right? So G quotient N is abelian. So for then what? Then for any x comma y in G, this xyn is equal to yxn, right? So this will imply what? This will imply this yx inverse xy belongs to n. This is by definition. And this is what? X inverse y inverse xy belongs to n. But this is what? This is how the elements of H look like. So therefore, H belongs to n. So these are the generators. So this is generators of H. These are all generators of H, by the way, here. And the moment something holds for a generators of a subgroup, it will hold for every other element of that group. So when I write this here belongs to N, which belongs to H. So these were the generators of my group H. And the moment I say that those generators are all inside my N, the entire subgroup will be inside my N, because N itself is closed under multiplication, closed under group operation, and that uh, close property of that group operation will also give us that H entirely contains inside N. So showing only the generators belongs to N was enough for us. And this happened because of This is true for any xy in G, and we show that this x inverse y inverse xy for any given xy in G belongs to N. Okay, I hope this is clear. Therefore, this is indeed a subgroup. So H itself was a subgroup, and now it is completely contained inside N. So it is a subgroup of N. So this statement that it is not a subgroup is false. It is a subgroup of my other subgroup, and H is a subgroup of this N such that G quotient N is abelian. So now the final statement that if K is a subgroup of G and H is contained in K, then we have to check whether K is a normal subgroup of G or not. So given that K is subgroup of G, H is subgroup of K, to show whether K is normal subgroup, show or check. Let me write show or check. K is normal subgroup of G. Okay, so how to proceed with this? Again, K is normal subgroup, so let K belongs to K and this small g belongs to G. We just need to check whether this G, K, G inverse belongs to K or not. That's what we want or need, or we need to show or check. Okay, so how to proceed with this? So again, this G, we have this G, K, G inverse belongs to K, right? Sorry, in G. And K inverse belongs to G. Then this K inverse G, K, G inverse, this belongs to H. But this anyway, H contains K. So this K inverse G, K, G inverse belongs to K. And the moment I have this, if I multiply both, I mean, if I multiply this, since this implies K, K, G inverse, this belongs to K, since K belongs to K. So again, I get this G, K, G inverse belongs to K. Therefore, my K is a normal subgroup of G. So this is quite strong statement. What it says is that K be any subgroup of G which contains H. The moment I have that, my group belongs to that. My group becomes normal subgroup of G. This is quite a strong statement. All it says that any subgroup of G which contains H becomes a normal subgroup of G. So any doubts here? It is happening from this property here. The way H is defined or has generators, it's happening from here. So any doubt? This is by definition of H. Okay, no doubts. Okay. Therefore, K is normal and this final statement is true and it is quite strong statement. Now, let us move to this next question. Question 4. Let let G is equal to Z belongs to C such that Z power N is 1 for some N in Z plus and K belongs to Z plus, then the map from G to itself by Z going to Z power K is. Now the options is injective, B surjective, C homomorphism, and D isomorphism. We have to check which of this is happening. First of all, see that this is G is equal to Z belongs to C such that Z power n is 1 for some n in Z. So this, they have just said that this is C, but this is G is a subgroup of C star under multiplication. Okay, please understand this. Because see, for no, 0 does not belong to this uh, set G for now. Okay, and yeah, so it is multiplicative, I mean, it is subgroup of multiplication set of complex numbers. So this C star is C minus 0. Here it's C. Any doubts here? The way G is defined. And the map is now from, let me call this map pk as before. Pk is from G going to, K is now fixed, G going to G. And what they are asking is that now my Z goes to Z power K. Now they are asking this G is injective, surjective, homomorphism, isomorphism, what it is. Can you, can we say something that will this be always injective, surjective, homomorphism, isomorphism? Any guesses? First of all, can this be isomorphism for any K? Injective, forget about isomorphism. Whether this map can be injective for any given K or not. Can you give me one element for any given K such that it will give me identity? Can we have the a surety that such element will always exist? See, we are my G is such that Z power n is 1 for some n, and but that still does not guarantee that for given K, I mean the structure, the definition of G does not guarantee for this happen. I mean there will always be some Z in C such that Z power n becomes I mean Z power K becomes my 1 for this K here or for this K here. Okay, but we are in complex number. So for any to a to check injectivity. So note that for any K in Z plus, We can choose kth root of unity, right? Kth root of unity such that omega k is 1. This we can always choose, right? And we have such elements in C. And if not, I mean, we have such elements in C, and if not, then we can have this polynomial. If you do not know what kth root of unity is, we at least know that C is algebraically closed. Okay, so if I want to find omega injectivity, I need to find an element such that its power becomes 1. So this polynomial px is equal to x power k minus 1. This px has a root if you don't in C. This is this we know. C is closed under I mean it's algebraically closed. So if I take this polynomial specific x power k minus 1, it will have some root, some non-zero root. Not non-zero, doesn't matter, non-zero, zero, we don't care. It has a root. It has root, and it is such that then we take that it has a root, say omega, then this omega power k minus 1 will be 0. So this will imply omega power k is 1, and then I have this pk of omega 1, and this imply my phi is not injective. Okay, so therefore my phi is not injective. Is this okay? K is any element in Z plus, and we have to check this for any given map phi k. So this is very generic. If you don't know kth root of unity, just ignore. Just keep this in mind. Okay, since K is algebra, see set of complex numbers is algebraically closed, we have this information with us. Is this okay? Okay. Now B, we have to check the surjectivity. To check P is surjective. Can you now guess how we are going to proceed with this? So we have to check the surjectivity. So let some Z be in G, and we need to find, or can we find Y, or what we call it, G in G, such that pk of G is Z. Can we find this always? Or let me write this. Can we find this? Okay. We can use the same argument here. So instead, earlier for injectivity, we wanted to find the W such that W power K is 1. But now we have Z in G, and I now want to find W or omega, W, not omega, W in G such that phi K of W, that is some this kth power of this W will be my Z. So I start with some Z. I need to produce this W, or if you don't want W, let us call this U. This U in Z such that this phi k of U is Z. That is, we need to find. Can we find U in G such that U power k is Z? This is what we need to find. And can we find this U? Can you tell me how to start with this? We just did something earlier. Okay, so what we will do is we will do the similar argument that C is again algebraically closed. Then for polynomial Px is equal to x power k minus z. Instead of 1, now I have this z has a root in C. Then suppose U is root of Px, then U power k minus z is 0. So this implies U power k is z. But what is U power k? This is phi of U. And that I get as a z. By definition of phi. Okay, so therefore, for any z in C, we obtained U in G. U in G such that P of U is my Z. So therefore, this P is surjective map. Is this okay? How we obtain the surjectivity? In both the cases, C being algebraically closed is used. This need not hold in general. Is this okay? If in doubt, please. Now the C part. This is a surjective. We have to check whether homomorphism. So since A is anyway not injective, so it can anyway be will not be isomorphism. For all isomorphism, we need both uh, injective and surjective. So anyway, yeah, something there was some problem. Yeah. So what I was saying is that if given phi is not injective, then it cannot be isomorphism. Because in order to have isomorphism, we need map to be both injective and surjective, but we already got that it is not injective, and we just not proved, but we obtained element which belong to my kernel for any given k. And so phi k is not injective. Again, we again proved that phi k is not surjective, and we again use this property, and we proved using this that this polynomial x power k minus z has root, and that root can be used as a pre-image of this element z here, or it can be used as an element in G such that under feed maps to Z. Okay, so this is there. Now we have to check whether this was group homomorphism or not. So for any x comma y in G, we anyway have pk of xy will be what? Xy power k. But since we are in complex numbers, multiplication is abelian. We get this x power k, y power k. This is my phi k of x and phi k of y. So therefore, this phi k is homomorphism. Any doubts here? Anywhere which is, if something is not clear, this is definitely homomorphism. Anyway, we were in abelian groups. Is this G was abelian group, and we also saw in earlier question that this map of this kind are homomorphism in abelian groups. So this was anyway homomorphism, and we anyway checked it here that it is homomorphism. So any doubts, please let me know. Not then, let us check. Question 5, that let G be a group such that this cardinality of G is PQ, where P and Q are prime numbers and P and Q need not be distinct. Then the possible values of ZG is, or first they are saying it's 1, B is P, C is Q, and D is PQ. This is all. And I hope we all know what this is center of my group X in G such that for all G in G, XG is GX. Okay, this is my center of the group. And now they have given that G is a group such that its cardinality is PQ, P and Q both are primes, but they need not be equal. So we could have cardinality of G as something like 9 or 25 and so on. They could be distinct, need not be distinct. Only thing which is given there, G is a group with cardinality PQ. PQ are prime. And now we have to find the possible values of cardinality of this center of group G. Any way we can proceed with this? Any idea how to try to solve this? Or is one possible? Cardinality of G being 1, is it possible? We have to ask the possibility of cardinality of ZG. So is it possible to have 1 as cardinality of ZG? Do you know any group where cardinality of ZG is just 1? We are just asking about possibility. So if there exists one group such that its center is trivial, then the possibility makes sense. So is 1 possible for ZG? Do we have any group where center of the group is ZG? Okay. So we know many such groups, right? One which we even discussed earlier was this group, S3, right? Center of S3 is just this one, the identity cycle or okay, so cardinality of ZS3 is 1. Possibility is there. So it's possible to have only one element which commutes with other elements of my group. Is this okay? One is possibility. You can have many other groups where you will have this. But for now, is this okay? We have to check the possibility. Do we have now about PQ? Can we have a group of cardinality PQ which so see, cardinality of G is PQ, and now they are talking about cardinality of ZG. So if I am saying that cardinality of ZG is PQ, then I need to have a group of size PQ which is abelian, right? This was for option A, and now for option D. So given that cardinality of G is PQ, and to check the possibility of mod ZG being PQ means uh, that we need to find an abelian group of size PQ or of order PQ. Do we have such group always? For any given PQ, do we have a subgroup of this? And in general, this was only for S3. Sn in general has a center E. Okay, center of is E always. So even for this, it doesn't matter. But for now, this is okay. So wait. This possibility of 1 is okay, but can we always produce a group of order PQ where only the only element in the center is identity element? Can we always produce that? So let me just write the question here. Question for, you can think of this, for any PQ prime, can we always find a subgroup G of order PQ such that only mod ZG is one, that is ZG is trivial. You can think of this, okay? Even I don't know. I just thought of this right now. If you have any answer to this, try to solve it. Otherwise, we can discuss this in the next tutorial or maybe when we have a time. Okay, think of this. Oh, okay, that is okay. But for now, this G is a PQ. So can we always have a abelian group of size PQ? Do we know such groups which are abelian and of size PQ? We can take ZPQ, right? ZPQ under addition. This is ZPQ is an abelian group and ZPQ is of and cardinality of ZPQ is PQ. And so which is anyway abelian, so Z of ZPQ will have cardinality PQ. So yes, this possibility is there. So from this actually got I had this question that for any given P and Q, we can always find an abelian subgroup of order PQ, that is ZPQ. But can we, for any given PQ, can we have a subgroup of size PQ such that the center is only this identity element? Okay, so try to think of that. Now the other options are P and Q. Is it possible to have a center of group of size P in this case? To check, cardinality of ZG is P. And any guesses here whether this is true or false and what will happen? Is this true or not? Can we have a center of a group of size P or Q? For now P, okay. Can we have a subgroup with center of size P and G is of order PQ? Is this possible? So note that if suppose cardinality of ZG is P, okay, suppose we have this, then ZG is anyway normal subgroup of G, then this G mod ZG makes sense, right? Okay, then but G mod ZG uh, is well defined. Let me write. But then cardinality of G mod ZG is what? This is PQ by P, right? So it is Q. And Q is now this is prime. So this imply so groups of order prime are cyclic. So therefore this G mod ZG is a cyclic group. And does this remind you of something which we did last week? This will imply that G is abelian, right? We did this last time. We proved this that if G mod ZG is a cyclic, then G is abelian too. Okay, and I think when we did this, we had restriction on the size of G. I think G was finite in that case. Otherwise, this does not hold. Let us check. Doesn't matter. For now, we are in finite setup, so nothing is a problem. Uh, okay, for now we have this G mod ZG cyclic group, then G is abelian. This holds. This is true. So this imply if G is abelian, this implies ZG is my whole G. And this implies size of ZG to be PQ. But this contradicts my assumption that G mod ZG is P. So this is not possible. What? So what is not possible? That cardinality of ZG being P is not possible. Therefore, similarly with Q is also a prime. And when I take quotient, this G mod ZG will be of size P. And again, P is prime, and we are again end up having cyclic subgroup, and that will give me abelianness of that will give me that G is abelian, and again the size of G will be is equal to size of center of G, and that will be PQ. So therefore this again will create a problem. Therefore it's not possible. Therefore similarly for P, only if mod of ZG is Q. So both of these is not possible. P and Q is not possible. So this is also one thing which you can remember. If size of G is P into Q, where P and Q both are prime, then size of center of G will always be either one or it will be whole group. That is PQ. Center will either be trivial or center will be the whole group G itself. That's what this information gives. That's what tells us about That's the information we get from this question. Okay. Any further doubts? I mean, any doubts, whatever we discussed. Now, question 6. Let no, the set A, comma A belong to S3 is a normal subgroup of S3 plus S3. Okay, this is the question, and we have to check whether this statement is true or false. Okay, so let us denote this H to be A, comma A in S3. I hope you know what this means, right? A, comma A, it means elements of this form. I mean, A is in S3 and we are taking tuple of that now. Okay, so they are asking whether this is a normal subgroup of S3, some S3 or not. What is your guess? Any guesses here? Do you think it will be subgroup, normal subgroup? Again, we will do the same thing. How to check something is subgroup? Let H belongs to H, G belongs to G, and then check whether this G inverse belongs to my H or not. Okay, so we have to choose, either we have to prove this or we have to give a counter example. So what is your initial guess, whether this will be true? So something needs to land in H. Means what? This is direct. This is direct sum, right? And or product, whatever you want to call this. But the moment I say that, this is internal direct product. So when I say that something needs to land in H, so when I multiply it with the elements from G, I need both the coordinates of this product to be equal. So can we wisely choose two elements from H and G, uh, such that when I multiply, I do not get some element in H. Okay, so this is not true. Okay, this statement is not true. Let me just write this. This is false. This is not true. Now we have to find the counter example. Give me some element from G and H such that this will not hold. The G H G inverse will not be in H. Okay, so let me give you these elements. Let H is equal to this 1, 2, 1, 2. This is transposition, and my G is this. See, I want two coordinates to be not equal. So I will choose element from G such that elements in both the components or both the coordinates are different. So let's just choose this 1, 2, 3, and this as 1, 3. And now we have to check whether what is, first of all, we have G, we also need to find G inverse. What is G inverse? It is 1, 2, 3 inverse and 1, 3 inverse. 1, 3 inverse we know it is 1, 3 again. Its transposition inverse is the same thing. What is inverse of 1, 2, 3? Inverse of 1, 2, 3 is 1, 3, 2. Okay, please remember this. Okay, because see 1, 2, 3 and it is 1, 2, 3, 1, 2, 3 and 1, 3, 2. This is 1 going to 3, 3 going to 1, 2 going to 1, 1 goes to 2, 3 going to 2, 2 going to 3. Okay, so this is inverse of 1, 2, 3. Remember this. If not, if you don't know. So now I finally need to find what is GH inverse. GH inverse is G is my 1, 2, 3, 1, 3. H is 1, 2, 1, 2. And G inverse is 1, 3, 2, 1, 3. And we will do the calculation in one go. We won't be spending. If you have any doubt, then please let me know. Then we can do it slow. So first we will do with second coordinate. For the second coordinate, 1 goes to 3. Here 3 goes to 3. And here 3 goes to 1. So I have 1 goes to 1 here. For 2 in second component, second coordinate, 2 goes to 2. Here 2 goes to 1. And here 1 goes to 3. So I have 2 goes to 3. Now here I have 3 goes to 1, 1 goes to 2, and here 2 goes to 2. So I have here 2. Okay, so this is my cycle here. So this is again a transposition 2, 3. Now the first one. What is this? Here it is 1 going to 3. 3 goes to 3 here, and here 3 goes to 1. So I have 1 here. Now my 2 goes to 1, 1 goes to 2, and 2 goes to, wait, is there some problem? Here I have 1 goes to 3, 3 goes to 3. Wait. This we need to take it as, let us call this a G inverse and this as a G, and I have here 1, 3, 2. Let us do this and check whether this gives us the required thing or not. 1 goes to 2 here, 2 goes to 1, and 1 goes to 3. Now this is working. Earlier one was not working, okay? Or if it was working, please check. But for now, this works. 1 goes to 2 here, 2 goes to 1, and here 1 goes to 3. And now for 2, 2 goes to 3 here, 3 goes to 3, 3 goes to 2. And now 1 goes to 3. No, no, we want 3. 3 goes to 1, 1 goes to 2, and 2 goes to 1. So I have this. So now this transposition is 1, 3. Okay, so this is what I get. And this definitely does not belong to my H. And please understand here, choosing this GH G inverse is not equal to GH. I mean, please check. In earlier cases, I think it was giving me some element from H. But this definitely does not give me element from H. Okay, so any doubts here? I hope you all know how this multiplication of cycles work. If any doubt, please let me know. So therefore, this H is not a normal subgroup. It is definitely a subgroup, but it is not a normal subgroup of G. Any doubts here? Okay, I assume there are no doubts. If there are any doubts, please let me know. Now we are moving to question 7. And again, this is false. This is not a normal subgroup. And now again, this is true false. If H is a normal subgroup of G, okay, and cardinality of H is 2, or order of H is 2, then they are saying that H is contained in ZG. That is, H is a subgroup of center of my group G. This is the statement. So is this true or false? Or what do you think? So here only thing given is that H is normal subgroup of G and cardinality of H is 2. And to prove that, or to check that H is subgroup of ZG. Subgroup or subset, doesn't matter. So any guess here whether this will always true? So we have to check. See, H has size 2. So this implies H has something of this. H is of this sort, right? A not equal to E. H is this, just. And if I want to say that H is contained in ZG, the only thing I need to check is whether this, to show H is in ZG, we need to check whether, anyway, GE is equal to EG, that's not a problem. And so we need to check whether this GA is equal to AG or not, whether for all G in G, GA is AG or not, whether this holds. We have to check this. For identity is not a problem. The only not problem, only thing which we need to check is whether this A here, whether this gives me AG is equal to GA for any element G from the group or not. And what is your guess? Will this always happen? H is a normal subgroup. So given that since H is a normal subgroup, let H belongs to H. Sorry, let A belongs to H and G belongs to G. Okay, this is there. So what does this imply? Since H is normal subgroup, G inverse belongs to H. This much is clear. So but H has only two elements. So this will give me G inverse is equal to either A or G inverse will be E. And if G inverse is E, then GA is G. What I'm doing is, let me just write this explicitly. G inverse G is equal to EG, and this will be GA is equal to G. But again, I can pre-multiply by G inverse, and it will be G inverse GA is equal to G inverse G, and this will give me A is equal to E. So that's not a problem. A is equal to E, very well. I mean, this is not possible actually because we just chose. I mean, that's okay, right? I mean, we just chose this A from H. Don't mistake it with, or let me just write X here instead of this A. X here and X here. This X, or is this confusing? No, let us keep that as it is. This A is in H. So A was my E. So I just chose some random A in H, and this is what I got. If this G inverse is E, then A becomes E. That's not a problem. So this, but now I have this. This G inverse is A. So this imply what? This GA and G inverse G is AG, and this GA becomes AG now. Okay, so in either case, A is equal to E. If A is equal to E, then this G inverse is E. This statement is true. That's not a problem. And again here, if this G inverse is A, then I get this AG is equal to GA. So therefore, AG is equal to GA for all G in G. This statement is true for every G in G. Therefore, and note that this will not, I mean, therefore, A belongs to my ZG. Therefore, E is anyway in ZG, and now I got A is in ZG. Therefore, my H is a subset of ZG. Okay. Any doubts here? Any doubts? Okay, I assume there are no doubts. If so, this statement is true actually. This statement is true. Okay. So now this next question, that how many surjective homomorphisms are there from Z8 to Z4. This is uh, internal direct product. Okay, so this we have to check how many homomorphisms are possible. Surjective homomorphisms are possible from this internal direct product of Z8 Z2 to Z4 direct product Z4. Okay, do you have any idea how to proceed with this, whether this is possible or not? So this Z8 Z2 is all those A bar B bar such that A bar belongs to Z8, B bar belongs to Z2, and here this is A bar B bar, or let me write C bar D bar such that C bar and D bar both belongs to my Z4. Do you have any, I mean, can we give any surjective homomorphism from this Z8 product Z2 to Z4 product Z4? Is this possible? First of all, first understand that both this group have, what is the cardinality of this group? Both the group have cardinality 16. Okay, cardinality of Z8 is 16 and sorry, not Z8. Cardinality of Z8 plus Z2 is 16 and cardinality of Z4 plus Z4, or this inner direct inner product, is also 16. Okay, first check the cardinality. If the cardinality of this is lesser than cardinality of this group, I mean cardinality of domain is lesser than cardinality of codomain, then anyway surjectivity will not, I mean it's not possible. Okay, so that's there. But in this case, both the groups have same cardinality. But can we say that we can have a surjective map from this group? Let me call this H and this called G. Do we have any surjective map from H to G? Is it possible? Can you give me one element which does not have any pre-image under any, what I can say, homomorphism? There are two surjective homomorphism. What are those surjective homomorphisms? How is that possible? Can you give where? What is pre-image of this? Note that the moment I have surjectivity here, I will also have isomorphism here because both of these are of same size. So when we say that these two will be isomorphism, the moment I have one surjective homomorphism, that will give me an isomorphism between these two sets. because these are sets of same cardinality. So what will be the, what I can say? Is this possible? Do we have surjectivity for these two elements? I mean, this between these two groups. Is this possible to have isomorphism? Because the moment I have surjectivity, because of the same cardinality, I will also have isomorphism. So are these two groups isomorphism? I mean, are these two groups isomorphic? Let me write that down. Since cardinality of H is equal to cardinality of G, if we have surjective homomorphism, okay, homomorphism between H and G, this will also give me, this will also give us the isomorphism between H and G. Are these two groups isomorphic? What is the maximum order of any element in Z4 cross Z4 direct product Z4 or this in this G? What is the maximum order of any element in this group? So no- note that for any A comma B, or since we are doing this C comma D bar in Z4 product Z4, order of this C bar comma D bar is less than equal to 4. Okay, because 4 into C bar for any element, okay? This C bar comma D bar 4 times, or let me write this 4, is this 4C bar comma 4D bar, and this is 0 bar comma 0 bar. So for any element, order will be less than equal to 4. Is this clear for now at least? For any given element, C bar comma D bar in Z4 uh, uh, cross Z4, we here, any element will have order 4 or less. Is this clear at least? But is that the case in this? Is order of A bar comma B bar less than equal to 4 for all A bar comma B bar in Z8 plus Z2? Is this true? Can we give me an element here which has order greater than 4? We can take this, right? 1 bar comma 0 bar. What is order of this? Order of this is 8, right? Order of this is 8 in Z8 plus Z2. But if isomorphism was there, the both the groups will have, they're essentially same as a group if we have isomorphism. If there is isomorphism, and if in a domain I have element of order k, in codomain I will again have element of the same order and vice versa. But here that's not happening. I have element, the maximum order of any element in this Z4, direct product Z4 is 4, but that's not the case here. So therefore, this is not isomorphism, and that's why we anyway won't have any surjective map, because we anyway saw that if I have surjectivity because of cardinality, I will get it. I will have isomorphism, but the isomorphism is not possible because of this order argument which we just gave. Is this clear what I'm saying here? So there are no two surjective homomorphisms possible. I mean, no homomorphism possible at all. No, homomorphism is possible. Identity, I mean, everything goes to identity. Uh, I mean, the trivial homomorphism, everything goes to the identity in Z4 and Z4. But no, we are not talking about that. There's no surjective homomorphism possible from these two groups, from G to H. Okay, so therefore, no surjective homomorphism possible from Z8, Z2 to Z4, Z4. Is this clear? Okay, great. So I still have some time. This quick question. I mean, we did this something of this sort in earlier. The order of element one bar comma two bar in Z30 plus Z20 is what? What is order of this element in the Z30 plus Z20? Can someone guess what this is? We did one formula, right, last time. Do you all remember what that is? If not, forget about the formula. What is order of 1 bar in 30 bar? It is 30 bar. It is 30, right? Order of 1 bar is 30 in Z30. And what is order of 2 bar in Z20? It is 10, right? So order of this 1 bar comma 2 bar will be LCM of this order of 1 bar and order of 2 bar. Okay, so LCM of 30 and 10 is, was it LCM or G? I think it's GCD. order needs to be 30. Okay, so it will be, I mean, after 10, the 1 bar won't give me the 30 again, 0 bar here. So the order needs to be 30 here. Similarly, if you check, if I want to calculate order of 3 bar and 2 bar, or order of this, then order of 3 bar is here. Order of 3 bar is 10, and order of 5 bar is 4. So what will be order of 3 bar comma 5 bar here? It will be 20, right? Because we are taking LCM here. And LCM in this case is 20. And here also, we have 20 as LCM. So I hope this is clear. So it is in direct product, the order is LCM of the order. Okay, I will put the formula here, but you can check this. So I hope this one is clear. You can easily find. I think we solved questions of this type earlier also. So if there are any doubts, please let me know. Otherwise, we can stop. Any doubts? No doubts. Okay. So anyway, we are uh, ahead of time. So let us stop here. If you have any doubts, please raise it in discussion forum, and we will try to answer those. Yeah. Thank you.